Edwin Hubble first discovered galaxies were moving away from the Milky Way in 1929 by realizing the more distant galaxies move faster away from us than the nearby ones. To measure expansion history, scientists used Type 1a supernovas as their standard candle.
One example of a standard candle might be a 100-watt light bulb. You could have a bunch of these things sitting around in your room at different distances from you. Then the more distant ones will appear fainter and the more nearby ones will appear brighter.
Type 1a supernovas are always consistently brilliant, no matter where they occur in space.
A supernova is the colossal explosion of a star at the end of its life. It just goes kabam! And it occurs when a dying star known as a white dwarf goes through a nuclear runaway and just literally blows itself to smithereens. We find the Type 1a supernovae in very distant galaxies, so they look really faint, and then we compare them with Type 1a supernovae in nearby galaxies whose distances were measured using Cepheid variables or some other technique.
Using these Type 1a supernovas, two different teams set out in the 1990s to measure the deceleration rate of the universe. But to capture supernovas as they occur, astronomers had to put the universe on surveillance.
You can compare this a little bit to perhaps surveying a casino. So all these cameras are on all the time, and most of the time they don't find much of anything interesting, but occasionally they find what they're looking for. You have to look at lots of galaxies. So what we did is we took large telescopes with cameras that have wide fields of view, about as wide as, say, the width of the full moon. And we took many snapshots of space using this wide field camera. And each snapshot contains tens of thousands of galaxies. And by comparing the apparent brightness of the distant Type 1As with those of the nearby Type 1As in nearby galaxies, we can get the distance of the distant galaxies and hence the amount of time that we're looking back in the history of the universe.
After the two teams studied the results of 60 Type 1a supernovas, scientists were shocked at their results. The universe wasn't slowing down, its expansion was speeding up.
We all expected that expansion to be slowing down with time, because after all of the galaxies are pulling on one another.
We were so confident we were going to measure the rate at which the universe was slowing down, and then we found, of course, a negative answer. The universe is not slowing down, it's speeding up, and this was just a big mystery.
That is really, really weird. You know, we expected to measure some amount of slowdown, and instead it's expanding more quickly. That's like the wrong sign, right? We were really afraid that we had gotten completely the wrong answer. We rechecked our measurements, we checked the analysis. A bunch of people on each of the two teams did the measurements and the analysis independently and kept getting the same result.
One of the greatest shocks in the world of cosmology just in the last few years has been the realization that our universe is accelerating.
This repulsive force driving the universe was called dark energy, an invisible energy that was nothing anyone expected or understood.
It suggests that over the largest distances in the universe, there's a repulsive effect that dominates over gravity.
And dark energy was creating space, taking galaxies along for the ride.
This energy that appears to fill the universe and stretch the expansion of the universe faster and faster with time is now known as dark energy. So here I throw the apple and initially it's decelerating and then dark energy makes it accelerate away from me. So you throw the apple and it just zooms away faster and faster with time.
Like the apple forever traveling into space, galaxies are being carried away as more space is created.
So if you could imagine, a classroom populated by chairs, and those chairs are slowly getting further apart from one another within a classroom. Because if all the chairs are being stretched apart, like in the expanding universe, no matter which chair you sit on, you will find all chairs are moving away from you. So the chairs are not really expanding. In fact, the chairs are the same size, really. What's happening is that the room is getting bigger. The space in between the chairs is being stretched apart.
More space is being created in between the galaxies. So you have individual galaxies remaining of constant size in a universe where all of space is getting bigger and bigger.
We constructed the universe with power, and we are expanding it.